So we're looking at trying to calculate energies from reactions. And there are going to be a lot of different ways. This type of this kind of calculation is using bond dissociation energies. How much energy does it take to break a bond? And so what we're going to do to calculate this, okay, is to take all the bonds that are broken minus all the bonds that are formed. And so we have to identify them, and we did that by looking at the Lewis structures. And so if we look at each Lewis structure, we identify bonds broken, we identify all the bonds made, we take those numerical values, and we calculate the overall reaction. And the energy value is in some sort of kilojoules, some sort of energy per mole of the reaction. Now, reactions that have a negative delta H are important, okay, because they are termed what are called exothermic. That means the bonds that are formed are stronger than the bonds that were broken. This means that the reaction will occur spontaneously. These reactions tend to want to go because we want to make stronger bonds. We want to give up more energy and be at the most stable conformation. Bond enthalpies and bond lengths, the number of bonds between atoms as they increase, they are held more tightly, closely together, meaning that there is more energy needed to break them. So if we take a look at this reaction, okay, estimate the delta H for the following reaction. All right, what are we missing to actually solve this? When I have to discover how many bonds are broken, bonds are made, what's missing? Just look at the reaction. Can you identify broken and made bonds? No, because we're missing some Lewis structures. Okay, and if I go through and I do all the Lewis structures, meaning I count up all of the electrons, I find the central atom, I make one, bind to the other, fulfill octet, okay, I get this for nitrogen. Stop. I get this for hydrogen. Okay, I have now drawn Lewis structures. Can I solve the problem yet? Is there something about this reaction that is still missing? It's not balanced. What is not balanced? Hydrogens. Am I balanced now? Do I have 4 hydrogens on each side? Do I have 2 nitrogens on each side? Great. Okay, now I can start to identify bonds broken and made. Is this bond broken? Is there an H to an N on the product side? No. So I've broken 1, 2, 3, 4 bonds because there are no N to H's. Is there a nitrogen to nitrogen bond in the product? Be careful. There is not a single bond, nitrogen to nitrogen, so I've broken this one. Okay? I've broken everything. Is there a nitrogen to triple bond nitrogen in the reactant? No. I've made that bond. Are there hydrogen to hydrogen bonds in the original? No. I've made those. Okay? Now, delta H is equal to the sum of what? Bonds what minus bonds what? Bonds broken minus bonds formed or made. Okay? All right, so the delta H here. Bonds broken. I have 4 N to H's plus I have 1 N to an N. All of that minus I have 1 triple bond plus 2 hydrogen to hydrogen. Okay, so if I mathematically do this, 4 times into an H, 163, plus the dissociation energy of nitrogen to nitrogen. Nope, I messed something up. I messed something up. Into an H is not 163, is it? It is 391. Okay. Stop. Stop. How far are we going to go back? Okay, 4. We're going back a lot. Stop. Okay, 4 times 391 plus, and into an N is 163, minus nitrogen and nitrogen is 941 plus 2 times H to an H, 436. All right, let's get to the old calculator. 391 times 4, 1564 plus 163, 1727 minus 941 plus 436 plus 436 equals 1813. Okay, 1727 minus 1813. 86 kilojoules per mole of the reaction. All right. As long as you have a list of the values, that will work. Okay. There is a list of values in CHEM-111 under the reference section. On the exam, we'll probably give you a little table like that with values when you do the exam itself. Okay. So that's the application of calculating it through using bond dissociations. A third way to find enthalpy of reactions, the energy of a reaction, is to do this. The delta H of the reaction is equal to all the delta H's of the products minus all the delta H's of the reactants. Okay? And so enthalpy, we need to know, is an extensive property. Okay? Meaning that the magnitude is directly proportional to the amount. This is where we get this value that's kilojoules per mole. And so it says, in this case, if this methane burns in oxygen-based CO2 and water, it will produce this amount of energy. Okay? That means if I have 1 mole of methane, it will give this much energy. But if by chance I react 2 moles of methane, the energy doubles. Really, what is going to happen is this becomes a conversion factor when you do calculations. So this is a brand new conversion factor. Now, this conversion factor, important, this number of moles always relates to any one of these reactants or products. And so if there was a coefficient in front of one of those, then that coefficient is also part of the reaction. We'll do it as a couple of examples. All right, this is an important, star this. This is very, very, very important. A reaction can be given to you in one direction. In this case, CO2 plus water produces methane and oxygen. That's just the reverse of what I just showed you. The same amount of energy, what happens to its sign? It's switched. When you refer to these energies, if you reverse the reaction, then you must change the energy sign. It is opposite. So to burn creates or gives off 802 kilojoules per mole, but the reverse reaction requires 802 kilojoules per mole. Second thing that is very important. What is changing between this and that? The state. I go from a gas to a liquid. Gases have lots of energy because the gas molecules are moving very, very rapidly. If they slow down, they become liquid water. If that happens, the process also has to give up energy. In this case, it is negative, and so it gives up an amount of energy. Now, if you've ever cooked, you can get burned. You can burn by grabbing an iron skillet. That would hurt. But you can get actually a worse burn by a steam burn. What happens is the steam, if it hits your hand, condenses into water. Okay, slows down, but all of that energy goes into your hand, and it's relatively a large amount of energy. Okay, and so we can have energy changes because of state. We can also have energy changes because if I reverse the reference material I gave you, the reaction and its energy, if I reverse it, I have to reverse the energy value. Okay, so delta H, the negative or the positive depends upon, does the energy produce energy, give it off, or does it absorb? And so, which process would be endothermic or exothermic? Okay, is A exothermic or endothermic? A is ice cube melts.
Is it receiving heat?
So for the ice to melt, go from solid to a liquid,
Endo?
it is an endothermic process. It has to absorb energy for that process to occur. Okay, butane. Butane is in a lighter. Shouldn't know what a lighter is or what's going on, but a lighter in and of itself. If the lighter burns in oxygen, is that exothermic or endothermic? Exothermic, because it is giving off heat. Okay. In this reaction, endo or exo? It's endo. How in the world do we know?
Positive.
It's a positive value. That's it. It shows you that it's positive. I'm adding energy into this. Okay, calculate how much heat is transferred when 45 grams of methanol are decomposed by this reaction. Look at the reaction. Is this CH3OH decomposing, breaking down into some things? Okay, it's referring to this reaction as stated. Okay, what do I start off with to do this calculation? Yeah, we got to figure out how many moles are there. Okay, but I'm not giving moles, but I'm giving grams, right? Of CH3OH. Well, can I change grams of CH3OH? I can. Can you? Okay, I'm going to do this real quick. 12 for carbon, plus 4 more for hydrogen, plus 16. That will not get you a correct number on CHEM-111, but this is a very quick calculation. All right, in this case, moles of CH3OH. From the equation, what is the number that's understood there? 1. 1 mole of this will require this much energy. Okay, that was important to look at the coefficient in the equation. So if I take 45, I divide it by 32, and I multiply it by 90.7. That doesn't look right to me. 45, yes, divided by 32 times 90.7. I come up with, and this 3 sig figs, 128 kilojoule process. Okay? And so the amount of heat transferred is 128, or it takes 128 kilojoules to do this reaction. All right? If the enthalpy change is 16.5 kilojoules, how many grams of hydrogen are produced? Okay? I start off with what I'm given, 16.5 kilojoules. Okay? And then I have a conversion factor here. It says 90.7 kilojoules, moles of hydrogen. What number do I put in front of that? A 2. Because the relationship is this. For every 2 of these, I'll get that amount of energy. Okay, so that's important. I had to account for that coefficient. Am I done with this problem? 1 mole of H2 is 2 grams, roughly. 16.5 times 2 divided by 90.7 times 2. Is 7, and how many sig figs? 3. Yep. Okay, that's what I got. All right, so this key in this one was deriving that there was 2 moles of hydrogen that is produced to that amount of energy. Okay, how many kilojoules of heat are released when 10 grams of CO2 reacts completely? 10 grams of CO2. Grams of CO2 is moles of CO2. 1 mole weighs, I think it's 44. 16 times 2 plus 12 is 44. Okay. In this case, there is a 1 mole of C. Oh wait, totally messed that up, didn't I? It's not CO2, it's carbon monoxide, which has a totally different. Carbon monoxide is 16 plus 12 is 28. Okay. Okay. Carbon monoxide. All right. And do you see something weird?
Negative, yes.
What did I do? What did I do in that problem that you might have not have done?
Make the 90 negative?
I made the 90 negative. Why in the world did I make the 90 negative? Did I just make that up?
No, the question says reacts.
Ah, the question says CO reacts. What does your equation say CO does? It is what? Produced. So the question refers to the exact opposite of the reference given. So I have to flip the reaction. And when I flip the reaction, what do I do to the sign of the energy? I flip it. All right, so these are very hard problems. You actually have to read it. Okay? You just can't look at the number and just do a calculation. You have to make sure that we're referring to the same thing. The reference material may not be exactly what you need. The reference material in that equation may not be balanced. Okay? and it may not be in the right order. So you might have to watch it. All right. In this case, hydrogen peroxide can decompose to water and oxygen by the following reaction. Calculate the value of energy when 5 grams of hydrogen peroxide decomposes. Does the question refer to the exact equation? Yep. And so if I do 5 grams of hydrogen peroxide, I change grams into moles of hydrogen peroxide. 1 mole, 3234. Oxygen is 16 times 2 is 32, plus 2 more is 34. Mole of hydrogen peroxide to that amount of energy. The number in front of the hydrogen peroxide in the equation is 2. So 2 of those will produce that much energy. So 5 divided by 34 times 6 and 3 sig figs later. Negative 14.4. Okay, so we're using this as a conversion factor. The big deal about using this as a conversion factor, 1, to make sure that the equation is referring to your question so that you can use the number straight up. Okay. Second, you have to relate the energy to the coefficient of the molecule or compound that you're referring to. And so in this case, the hydrogen peroxide is what we're referring to. The equation had 2 moles to produce that number of kilojoules. And so this is a conversion factor with a little bit of interpretation, but no more than a conversion factor type of question. All right. 4th way to find the enthalpies of formation. All right. We're going to define something called delta HF, or it's the enthalpy of formation. It's the amount of energy needed to form 1 mole of that compound. Okay. Well, there's also something called the standard state conditions. The standard state is 1 atmosphere and 25 degrees Celsius, or 298 degrees Kelvin, or 298.15 degrees Kelvin. And so if I have the standard energy of formation, if I have the state of formation and the standard state, then the delta H0F is the standard state of formation. How much energy does it take to create 1 mole of this compound under the standard states? And there's a big list. You'll find that on CHEM-111 in the reference material. Okay, here's a small chart. All right. Here is the trick to this one. Elements have a standard state of 0. God made them. We do not have to add any more energy to make the elements themselves. So if you ever see an element, its standard state is 0, you will not find it in the chart most of the time, because they assume you understand that elements were formed by nature. We didn't have to react them. If you take a look at standard states of formation, a lot of them are negative, but not all of them. Some of them do require energy to form. Many of them give off energy when they do form.
Dr. D, I have a question.
Yeah.
Does it require us to know the state that they're naturally found in? Because I see diamond, which is carbon, a solid compressed, and it has.
Yeah, that's a good point. With these formations, you do have to understand what state they're in. And so the equation will most likely give you the state of matter so that you can do the calculation correctly. Here's where you see it most often. The formation of water. Most of the time people think it's liquid, and most of the time it is, but the value for liquid water and for gas water here, just slightly different. Just enough to make it a red box on CHEM-111. Okay, and so when you look at these, you do have to make sure you know what state it is in, because that will change the energy values. All right, so something explicit has to be in the equation for you to know that. So you're probably going to get an equation on the exam that shows everything out, both the compounds and the state. Okay. When you do this to calculate them, it's this. The delta H is equal to the sum of all the products multiplied by their coefficients minus the sum of all of the reactants times their coefficient. And so in this case, the delta H of the products and the delta H of reactants, if you take a look at this, products final minus reactants initial. This is probably the most often mixed up thing on this problem, is people just drop them down straight. It is products minus reactants. Okay, and so in this case, I'm going to look up the value of CO2, the value of water, but in its liquid state, and there's two of them, so I have to put a 2. Minus methane, its energy, and oxygen, its energy. Okay. In the next case, I look up CO2, and carbon dioxide is this number. I look up water in the liquid state. That's this one, and I have to use the 2 minus the methane, and methane is on here as minus 74.8, and I only have one of those. And oxygen is not on my list because it is an element, so it is a 0 value. And then to calculate all that, here's also kind of what really gets me. People will get to this point and then they'll get it wrong. They'll have it perfectly set up and they watch out for order of operation. Okay? All of this must be done, and then all of this must be done, and then you take the value that is this minus the whole value there. All right? You don't want to do all the work and identify everything and just not put it in the calculator right. I've seen too many people who have it perfectly set up, and I've got it wrong. Okay? So if we take a look at this calculation, the values for each of the compounds are above, and so I take products minus reactions, so the delta H is equal to the products, the energy of magnesium hydroxide plus water that is liquid minus the magnesium, so magnesium oxide, and then on the side magnesium hydroxide. So that plus 285.8, that's a negative. Oh, booger. I think that is supposed to be a negative number. Shoot. Okay. Here we go. Let me make sure that is true. Okay, magnesium. Yeah, here's where that list is. It's a long list. Magnesium, yeah, 601.8. It's a negative sign. So, oh, booger. So it is going back. I lost all my work. Minus 608.1 plus minus 285.8 minus 92.7. All right. Look at all those minus stuff. 601.8 plus 285.8. No. 0.8 plus 285.8. Yes. Minus. Okay. Okay, so 37.1 kilojoule. All right. And you're done. So you're going to either be given a table on the exam for these, for the values. On Chem-111, you'll have to look up that long reference sheet for all of them. Make sure you watch out for states of matter because that does change the values a little bit. Okay. Oh, good Lord have mercy. Oh, here we have to identify to calculate these all the values. Hydrogen is an element, so that's 0. Copper is an element, that is 0. I would have to look copper oxide up in a table, minus 156. And look up water in the liquid state, that's minus 285.8. And the calculation should be minus 129.7 because I take the products, 0 plus minus 285.8 minus 157.1 plus 0. Oh, I like that one. And so 285.8 negative. And that comes out correct. Okay, that was a fourth way. Okay, the fifth way to calculate things. Now, why in the world do we have all these different ways to calculate? Because sometimes, like the heats of formation, we actually need the value for the energy to form. Sometimes we don't have that. Sometimes it's not in the table. So we might have to use a different pathway to actually calculate that. And so there are different ways to calculate these things. Now, a lot of times you can tell what's going on or how to calculate these. Hess's law will most likely tell you that it's a Hess's law in the actual question using Hess's law. Here's the thing about Hess's law. If there are multiple steps in a reaction, okay, the delta H for the overall reaction is the sum of the energies of each one. So if you take the energies of every single reaction and you add them all up, it's exactly the same. And so here we have this. We go from the reactants to the products. Okay? But there is an energy that would take and break apart the C3H8, and that's the first reaction. Then we can form the CO2, that's the second reaction, and then we can form the water, that's the third reaction. If I add this value, and that value together, they will equal the overall value. All right, now when you add up the reactions, what you have to do is you have to add the actual energies, but you also actually have to add up the reactions themselves. It looks like this. Okay? Ooh, look at that. That is nasty. Okay, H1. That's the first reaction. C3H8 plus 5 oxygens create 3 carbons, 4 hydrogens, and 5 oxygens. There's the energy at the end. Now, I told you we can add that number, that number, that number, and come up to this number. That's fine. But we also have to add up the reactions. The reactions must equal the overall reaction. Now, we do this by doing this. If you have something on the reactant side and the product side at the same time, then they really didn't do anything. So this graphite here is on the reactant side and on the product side, exactly 3 of them. Okay? And let's see. We have other things that we could cancel out. All right. We have on this H2, 8 of them. And on this side, I have 8 of them. I can get rid of that. Is there anything else I can get rid of?
3 CO2.
There's 3 CO2s here and 3 CO2s there. I can get rid of that. But I can't get rid of this. Do you see that? Okay. Anything else I can get rid of? What is it? Yeah, O2s. I can get rid of 5 of them here, and 5 of them there, and 2 of them there, and 2 of them there. But I can't get rid of that, right? Because there's not enough on the other side. So what am I left with? I'm left with this, which is that. 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 And so I have added up the 3 reactions, and it added up to the end. And I'm left with my overall reaction. Okay? Now, it's not going to be as simple as that sometimes. Okay? Now, you can use Hess's law. It's a long problem. You can also use these. And check this out. The delta H of formation, all the products minus the reactants, comes out to the same number. I'd rather use this one if I can. The problem is I may not have these numbers. Hess's law is actually used to actually calculate some of these numbers themselves. And so sometimes, even though you could do it different ways, you don't have enough information to do it once, so you have to do it different. All right. Now, in this case, if I want to do products minus reactants, okay, the problem is I don't have a value for B2H6, so I can't do that. But I do have these 3 reactions together. And so I can use Hess's law to figure out what's going on. All right, some keys. Oops. Some keys to this. All right. If I add up these 3 things, do I get what I want? Well, what in the world do I want? I want to make B2H6. But a formation, an enthalpy of formation is to take the elements that are part of this and create the final product. And so the elements that are used are boron plus hydrogen to yield B2H6. Now, is that equation balanced? No? What do I have to put in front of B? What do I have to put in front of the H2? 3. That is what I want to have the reaction add up to be. Okay, to find out how much energy it takes to make B2H6. That is my goal, to get to 2 B's plus 3 H's yields B2H6. Okay, I'm given 3 reactions. All right, here's some clues. I can flip reactions if I need to, based on what I'm given. But if I flip the reaction, what happens to the sign of the energy? It changes to the opposite. Also, I don't have to use all of the reaction. I might only need to use half of it. If I use half of the reaction, how much of the energy did I use? Only half. Okay? So, I can flip them, and I can use parts of them or more than one of them. All right, let's try this. Okay, remember, what is my goal? 2 B's plus 3 H2's yield B2H6. Okay, where's B2H6? Which equation? The third one. Is B2H6 where I want it? No. It's in the reactant. I want it as the what? Product. So I have to take this reaction, number 3, and I've got to flip it. Now, also, how many BH26s do I need? How many of them? I only need 1, right? This equation has 1, so I don't have to do anything but flip it. So I'm going to do B2O3 plus 3 waters yields B2H6 plus 3 oxygens equals now 2,147 negative. So that's how much energy. I've got B2H6 on the correct side. All right, I've used 3. Now, look at equation 1. All right. Equation 1 has boron, which is on the correct side, right? So it's in the right side, and that's the only place boron goes. So I'm going to use it as written, but do I use it exactly as written? Do I need that entire reaction? No. How much of it do you need? Do you need all of it? How many borons are in that whole equation? 4. How many do I really need? 2. I'm going to use 1/2 of that entire reaction. All right? Oh, don't do this to me. Okay. So for the delta H of 1, I'm going to use exactly 1/2 of it. That means I get 2 borons plus, 1.5 oxygens, okay, and 1 B2O3, okay, and I get exactly 1/2 of the energy of that. Okay, which is 2509.1 divided by 2. Negative 1254.55. Okay? I need hydrogen. Where's hydrogen coming from? Equation which? Equation 2, right? All right, how many hydrogens do I need? H2s. I need how many? 3. All right. The equation gives me how many? 2. So I need one of those equations, and then I need how much more of that equation? Do I need how much? 1/2 more. So I'm going to multiply equation number 2 by 1.5. The reason 1.5 times 2 is 3. That's how many H2s I need. So 1.5 times 2 is 3. 1.5 times 1 is 1.5 O2s. I create 3 waters, and the energy now is 1.5 times minus 571.7. Uh-oh. There's something going on here. I messed something up. Tell me where I messed up on the energies.
We're supposed to put the first one as a positive.
Ah, the first one needs to be what? Positive. Why? Because I reversed it.
I was a little confused.
Okay, now, let's see if we got it right. All right, on this side, I have B2HO3, and on this side, I have B2HO3. Get rid of those. Anything else I can get rid of? What is it? 1.502s. I've got 1.502s, and I got another 1.502s to make how many? 3. And on this side I have 3. Get rid of them. Anything else? 3 waters on this side, 3 waters on that side. Get rid of those. What am I left with? I'm left with 2 borons plus 3 H2s yields B2H6. So the energy for that, the first energy is positive, the second energy is negative, the third energy is negative. So I take 2,147.5, subtract 1,254.55, subtract 857.55, 35.4 kilojoules for this problem. Oh my goodness. For this problem, you had to know where you're going. You had to have an equation by which you were making all of your decisions about how to use each of the reactions. Okay? Whatever you do to the reaction, you have to do to the energy. At the end, you add up all the energies. Okay, here's what CHEM-111 can do to you. It can give you 3 equations, of which you don't even need one of them. If you're given extra information, what do you do with it? You get rid of it and throw it away. Okay? Most of the time, you'll give in 3 equations. You've got to use all of them. Most of the time. Okay? Every so often, they will give you more information than you need. Don't be confused with that. How do you know you can do one of these things? You just have to try it out.